Somewhere beyond the familiar boundaries of our solar system, buried deep within the constellation Cygnus, lies a star system that challenges everything we thought we understood about where moons can exist and how large they can grow. The universe stretches outward in every direction, filled with billions of galaxies, each containing hundreds of billions of stars, and orbiting those stars are worlds beyond counting. Among all those countless worlds, one particular discovery stands apart. Not a planet, not a star, but a moon. A moon so enormous, so far from home, and so unlike anything in our cosmic neighborhood that scientists are still wrestling with what it truly means. This is the story of Kepler-1708b, a candidate exomoon circling a gas giant nearly 5,000 light-years away, and a discovery that may forever change how humanity thinks about the diversity of worlds hiding in the dark. What makes this system extraordinary is not the planet itself. It is what appears to be traveling alongside it. Kepler-1708b is a gas giant exoplanet discovered through data collected by NASA's Kepler Space Telescope, a mission designed specifically to hunt for planets by watching stars for tiny dips in brightness caused when a world passes in front of them. This technique, called the transit method, has revealed thousands of planets, but Kepler-1708b caught the attention of researchers for a different reason entirely. The planet itself is enormous, roughly 2.5 times the radius of Jupiter, making it one of the larger gas giants ever catalogued. It orbits its host star at a distance considered to be within or near the habitable zone, the region where conditions might theoretically allow liquid water to exist under the right circumstances. The star it orbits is slightly cooler and dimmer than our own Sun, which pushes that habitable zone outward compared to what we experience in our solar system. In 2022, astronomers David Kipping and his team at Columbia University published findings suggesting that Kepler-1708b hosts a moon, and not just any moon. The candidate exomoon, designated Kepler-1708bi, appears to be roughly 2.5 times the radius of Earth. To put that into perspective, our own moon has a radius of about 1,737 kilometers. This proposed exomoon would dwarf it entirely, sitting closer in size to Neptune than to anything we would traditionally call a moon. If confirmed, it would be the largest moon ever discovered relative to its host planet, and one of the largest natural satellites ever identified anywhere in the known universe. The detection came from careful analysis of transit data, a secondary dip in the star's light that appeared to trail behind the planet's own transit signal, consistent with what a large moon in a wide orbit would produce. The signal is subtle, and the scientific community remains cautious, but the data is compelling enough that it has sparked serious debate and ongoing investigation. Standing on the surface of Kepler-1708bi, if standing were even possible, would be one of the most alien experiences imaginable. The moon is likely composed of gas or ice rather than solid rock, given its enormous size and the physics governing how large moons form and maintain their structure. However, theoretical models allow for a range of compositions, and some scientists speculate that beneath thick atmospheric layers, denser regions could exist. The sky above this world would be dominated by the overwhelming presence of Kepler-1708b itself, a gas giant so massive that it would fill a significant portion of the visible sky, its swirling cloud bands and atmospheric storms casting reflected light across the moon's surface during the long orbital night. The host star, dimmer and cooler than our Sun, would appear smaller and redder on the horizon, bathing everything in a warm amber glow. Temperatures on the moon would depend heavily on its atmospheric composition, the greenhouse effect of any gases present, and the tidal heating generated by the gravitational interaction between the moon and its enormous parent planet. Tidal forces from a gas giant of that scale would flex and compress the moon's interior continuously, potentially generating significant internal heat. a process we see at work right here in our own solar system on Jupiter's volcanic moon Io. Detecting a moon around a planet nearly 5,000 light-years away is an almost incomprehensible technical achievement. The Kepler Space Telescope stared at over 150,000 stars simultaneously for years, measuring their brightness with extraordinary precision. When a planet transits its star, it blocks a tiny fraction of that starlight, sometimes less than 1%. A moon orbiting that planet creates an even smaller secondary signal, often appearing slightly before or after the planet's transit, depending on where in its orbit the moon happens to be at that moment. This timing variation, combined with additional dips in the light curve, is what researchers look for when hunting for exomoons. The challenge is immense because noise in the data, stellar activity, and instrumental artifacts can all mimic the signals that moons would produce. This is why the confirmation of Kepler-1708 remains pending. The signal is there, it is consistent with a large moon, but ruling out every alternative explanation requires more data than currently exists. Future telescopes, including the James Webb Space Telescope, may eventually provide the resolution and sensitivity needed to confirm or rule out this extraordinary candidate once and for all. The universe may be full of such worlds, hidden in plain sight around gas giants, that we have long assumed to be barren and inhospitable. First and most immediately, it would prove that moons can form and survive around gas giants in wide orbits far from their host stars, expanding our models of planetary system formation significantly. It would suggest that the process of moon formation is not limited to the compact, orderly arrangements we see around Jupiter and Saturn, but can produce enormous satellites in configurations we had not previously considered stable over long timescales. Second, it raises profound questions about habitability. A moon of this size, orbiting within the habitable zone of its star, could theoretically maintain conditions suitable for liquid water, particularly if tidal heating supplements the energy it receives from the distant star. This would make it a candidate for life, not in the way we typically imagine planets as hosts for biology. The Kepler-1708 system drifts in the darkness of the Milky Way, nearly 5,000 light-years from the small blue world where curious creatures first learned to look upward and wonder. The distance is so vast that even travelling at the speed of light, 186,000 miles per second, the journey would take 5,000 years. Every piece of information we have about this system arrived here as ancient light, photons that left their source long before recorded human history began. And yet, from that ancient light, scientists have extracted the outline of a world, a giant moon circling a giant planet, circling a distant star, in a galaxy that contains more stars than there are grains of sand on every beach on Earth. The discovery of Kepler-1708 confirmed or not, reminds us that the universe is stranger, larger, and more varied than our imaginations naturally reach. Every new detection, every careful analysis of a light curve, every debate among scientists about what a signal truly means, all of it pushes the boundary of the known just a little further into the unknown. And somewhere out there, in the dark between the stars, worlds beyond counting are waiting to be found.